Hello everyone. Now I'm going to explain you about equivalence relations. So, equivalence relations. In this, I'll assume that you have some idea about relations. I assume that you have idea about reflexive relations, symmetric relations, and transitive relations. So, equivalence relation is a relation which is reflexive, symmetric, and transitive. So, if a relation satisfies these three relation conditions, then it can be said as equivalence relation. So, the important thing to note here is in the equivalence relation, the domain, for suppose equivalence relation here is R. So, the domain of R will be the set on which this relation is applied. This relation is applied. So, domain of R equals to set on which this relation is applied. This is an important note you have to remember. And you also remember that R is a reflexive, symmetric, and transitive. We'll go through some examples. We'll understand in more detailed fashion. Okay, suppose A is equals to 1, 2, 3, 4. Set of 4 elements. So, for example, consider R the relation applied on set A to be 1 1 1 2 2 1 2 2 2 3 3 4 3 3 4 3 and 4 4. So these are the ordered pairs in the relation R. So we now have to check whether this relation R is an equivalence relation or not. So an equivalence relation satisfies reflexive, symmetric, and transitive properties, or you can also say relations. So for the reflexive relations, we need to have 1 1 2 2 3 3 and 4 4. So we have 1 1 here, and we have 2 2 here, we have 3 3 here, we have 4 4. Along with this, we have some other order pairs. We need not remember, we need not check whether order pairs are of particular type. I mean, the order pairs can be anything. So first, if a relation needs to be reflexive, then it should have all the elements of the set as same x and same y. So here we have 1 1 here, 2 2 here, 3 3 here, and 4 4 here. So that ensures us this is reflexive. This is reflexive. Next, check for symmetric. So if we have 1 1, if we flip the positions of x and y, we get same 1 1, and it's there. If we have 1 2, if we exchange the positions, we get 2 1, and we have 2 1 here. 2 2 2 2. If we flip the exchange or exchange xy, we get the same. 2 3. Sorry, there is no 3 2 3 here. So 3 4 and 4 3 and 4 4. So this is the thing. It satisfies symmetric property. Now we need to check for transitive property. 1 1 2 1 2. So 1 1 1, we should not check for the pairs that are reflexive. We should check the pairs that are not reflexive. So 1 2 1 2 on 2 1. So 1 1, we have 1 1 here. So 1 2 on 2 2, we have 1 2 here. Hope you're understanding. So 2 1 on 1 1, we have 2 1 here. 2 1 on 1 2, we have 2 2 here. 3 4 on 4 3, we have 3 3 here. 4 3 on 3 4, 4 4 4 4 here. So this is a transitive relation. So what we can say is the relation R is equivalence relation. Hope it's clear. Okay, so the relation is equivalence relation. Okay, next we try to do this the same thing using digraph. Digraph method to find, to know if it is equivalence or not. Equivalence or not. Equivalence relation or not. So digraph method, we use a graph, a directed graph. Di means directed. So we have 1 1. So first make the nodes 1 2 3 4. So 1 2 3 4. So 1 2 3 and 4. Cannot, you can take in any order, it's not a problem. Okay, so we have edge from 1 to 1. You can keep it like this. 1 to 2, I'm referring this. So we have edge from 1 to 1. So 1 to 1, we have self loop here. So we also have edge from 1 to 2. So we can keep 1 to 2 here, and 2 to 1, there's an edge. Next 2 to 2, this is a self loop, and 3 to 3 and 3 to 4 and 4 to 3 and 4 to 4. So in order to this is a digraph of the relation R. Okay, so we need to check whether this relation R is equivalence relation or not. So in order to confirm that this is a equivalence relation or not, first we need to check the self loops of all nodes. So first node we have self loop, second node we have a self loop, third we have self loop, fourth also we have a self loop. So all four nodes are having self loops. That means it is reflexive. R is satisfied. And next, symmetric. If we have 1 2, we should have 2 1. Yes, it's there. If you have 4 3, we should have 3 4. Yes, it's there. So symmetric is also satisfied here. So next, transitive. If you have 1 to 2 and 2 to 1, you should have 1 to 1. Yes, it's there. If you have 2 to 1 and 1 to 2, you should have 2 to 2. Yes, it's there. If you have 4 to 3 and 3 to 4, you should have 4 to 4. It's there. You should have, if you have 3 to 4 and 4 to 3, you should have 3 to 3. It's there. So it's reflexive, symmetric, and transitive. Therefore, we can say that R is equivalence relations. So first we have started with the basic conditions that are that a, a relation needs to have in order to become an equivalence relation, that is reflexive, symmetric, transitive. And we also discussed a node in which the domain of R, if R is a equivalence, the set domain of R will be the set on which this relation is applied. So for example, uh, I'll just prove this. I'll just prove the statement by taking this example itself. So the domain of R here can be obtained from 1 is a set of the x coordinates of all the order pairs 1 1 2 2 3 3 4 4. So if we group a set, what we get is domain of R is equals to 1 2 3 4. This is exactly the set we applied on. This is equals to A. So the domain of R is equals to A. So the node which we have given earlier is true. So this is what we discussed. We had discussed using two methods, digraph method and a simple checking method. Sometimes the digraph method is preferable. I think it's most of the time it's most preferable. So it's better if you, it's your choice. If you take the digraph method, it's easier to analyze. You won't get confused. So it's better if you choose the digraph method. The first method is also easier one, but we don't have any visualization of that, so it's not that easy. But with some practice, you can do the first method, and it may seem easier for you. Okay, thank you.